So last class, we talked about how to determine the final temperature of a mixture of water, like a mixture of two different temperatures of water. Like in number 16, there we go. In number 16, we had these two samples of water that had the same masses, but their temperatures were different. So to find the final temperature, all you had to do is take the straight average, like what you just did in your lab, assuming that no energy was lost to the surroundings, like through the calorimeter or anything like that. All right. In number 17, we couldn't take the straight average because our masses were different. And if you recall, for this one, we had a lot more of the colder water than we did of the warm water. So our final temperature ended up being closer to that colder water. I think it was like 23 degrees Celsius, what we calculated last class. For number 18, what is the same? Our masses. Mass is the same. But what's different? The substances, which means our specific heats, are different. Now, the reason this is an S and not a C is just because it's a metal. Okay, but it's the same thing. It means the same thing. So now, recall from last class, what is the relationship between the amount that the temperature changes and the specific heat of the substance? They're inverse. Yay! As when you have a really low specific heat capacity, that means that the temperature is going to change a lot more. Okay? So, for this problem, we have an iron ball, right? It's iron, yeah, an iron ball that's at 90 degrees Celsius. So it's really hot, and we're plunging it into water that's at 10 degrees Celsius. So, iron has a much lower specific heat than water. So what can be said about our iron and its temperature change? It's going to be a much larger temperature change than our water. Remember, water resists changes to temperature a lot. Okay? So our final temperature is going to be closer to the initial temperature of which substance? The water. So our final temperature, what would we say our answer is? A, B, or C? C. Because our water starting off at 10, that iron is going to not really heat up that water too much. Okay? But then we can actually calculate what that change in temperature is. Now remember, answering the multiple choice question is a perfectly valid multiple choice question, like on the AP exam, on our 6 and 9 quizzes, on our tests. Doing the calculation, though, typically requires a calculator, so that I would not hold you responsible for on a test or quiz. Okay? So let's set up the problem. When we're doing these calculations, what's our formula that we're using? Well, we can use Q equals MCAT, but because we have two different substances, we have to do MCAT twice. So that's when we did the combined formula. Negative MCAT equals positive MCAT. Yeah? Where negative MCAT is the stuff for the substance that's losing energy, and positive MCAT is the stuff for the substance that's gaining energy, because the energy that's lost by the iron ball is going to be gained by the water. Okay? So, what cancels out? Mass. Mass cancels, because it's both 50 grams. Now, we could do the math with the mass, but just save it, make it easier for yourself. I don't understand what you just said. So C for the metal is the 0.45. T final is what we're solving for, right? What was our T initial for the metal? 90. What's C for water? It was given in the problem, but you are memorizing that. T final minus, what was the initial temperature of the water? 10 degrees Celsius. Now I'm going to walk through the algebra on this one just so that I can clear up any misconceptions that we had from last class, or issues from last class. If it makes your life easier when you're doing math like this, when you're doing algebra, get rid of the units. Because sometimes those units can be confusing. And they, also it's so much more to write. So just get rid of the units. And let's make t final x. Because then we turn it into a math problem, which you've been seeing since, I don't know, like you were born. Right? So we're going to distribute 0.45 through the t final, or x minus 90, but we have a negative, so we're going to have negative 0.45x. What's a negative times a negative? Positive. So plus 0.45 times 90 is 40.5. So we're done with the left side. Now for the right side, we're going to distribute 4.18 through. So we're going to have 4.18x minus, what's 4.18 times 10? 41.8. And now we're going to combine like terms, move things over. What I did is I moved my constant value over to the left and my x value over to the right. So I get 82.3 equals 4.63x. And now how do we solve for x? Divide by 4.63. Now in terms of sig figs, if you're looking at your temperatures, notice that we only had 2 sig figs for both of those. We were significant to the ones place. So our answer is going to be significant to the ones place. So what do you get? 18, yeah? So that's our final temperature. Hold on 1 second. Any questions? Is 18 degrees between 10 and 50? Yes. Yep. So good. Cool. All right, on to number 19. I said last class that the more challenging part of this unit is, when you're doing these calculations, is the sign, positive or negative, has to do with from what viewpoint are you doing the calculation, okay? That's always the hardest part with this, is figuring out, is it positive or negative based off of the viewpoint of what I'm doing the calculation from, okay? So for this one, we have 1.095 grams of sodium hydroxide is dissolved in 150 grams of water that's initially at 23.5 degrees Celsius. And that's in a coffee cup calorimeter. The final temperature is found to be 25.32 degrees Celsius. We're going to calculate the heat liberated when sodium hydroxide dissolves in water. And we're also going to assume that the specific heat of the solution is same as that of water and that no heat is absorbed by that calorimeter. Our next problem, we're actually going to account for heat being lost through the calorimeter. But for this one, we're assuming that our calorimeter is perfect and it does not lose any heat. Okay. Let's think through this problem. We're dissolving sodium hydroxide in water. What's happening with heat? What does it say right here? Liberated. What does that mean? I'm not talking about we're making it free. It's not political. It's just, it's being lost, right? The sodium hydroxide is producing heat as it dissolves in water. Okay? So how can you describe sodium hydroxide dissolving in water? It's exothermic. So its delta H should be negative. Okay? Let's write that down. I can write exothermic, negative delta H. When we do our calculations, we're going to get a positive Q, but I'll explain why in just a little bit. Okay? So, let's just start off. This is calorimetry. So what's our formula? So we're not going to use negative MCAT equals positive MCAT only because we're not mixing two things that are starting at different temperatures. We can just use Q equals MCAT. Because both the sodium hydroxide and the water, we're just mixing them together, but they're starting off at an initial temperature, the same initial temperature. And then it's raising the temperature because it's producing that heat. Okay? So it's just one Q equals MCAT. What is our M? Yes, M is mass. What is our M in this problem? It's going to be the total mass of both the sodium hydroxide and the water. So our M is going to be 151.095, right? I'm ignoring sig figs for right now. We can deal with it at the end. I know. We're just doing it at the end. Okay. What? We're not solving for C. We have memorized C, so it tells you, shh, guys, it tells you that we're assuming the specific heat of the solution is the same as that of water, so 4.18. Now our delta T, we know that, but let's write out, what's our final temperature? 25.32. What's our initial temperature? -23.50. Thank you. All right, go ahead and calculate Q. Calculate Q. What do you get? So when we subtract our temperatures, it's limiting us down to 3 sig figs. So 1,150. No, because you're only going to the second decimal place when you subtract these. Subtraction has different rules from multiplication and division.
It's the same as addition, right?
Yes.
So doesn't the second one have 2 on the right side of the decimal?
Yeah, when you subtract these, the difference is what? 1.82?
Okay.
Yeah, that only has 3 sig figs.
Yeah.
So the rule, remember, the rule for sig figs, so technically we are supposed to round off for sig figs when we change the type of rule we have. So multiplication and division have different rules from addition and subtraction. So if you switch from like adding or subtracting to then multiplying or dividing, you're supposed to round off between. In physics, they say just round at the end because they mostly deal with multiplication and division anyway. So here, technically, we were supposed to round for sig figs with our mass and then also with our temperature before we multiplied. But we found out last class that if we had used 151.1, it wouldn't have actually changed the final answer. Okay. Nope, it's a constant. The 4.18 does not count. What's our unit? Joules. All right. So I told you we were going to get a positive Q even though we know this is exothermic. Why? Why is Q positive? Your sentence was almost there until the last word you said. What's in our surroundings? What's measuring the temperature? The thermometer, right?
The thermometer's in the water.
Is our thermometer part of our system? No. It's part of the surroundings. It's an outside observer. So, okay, let's think about this. In order for the thermometer's temperature to increase, does the thermometer have to gain or lose energy? It has to gain, right? So in order for the thermometer to raise its temperature, it has to gain energy. Where is the energy coming from? The system. In this case, the sodium hydroxide dissolving. Okay? Okay, so this is where it gets tricky. In when you're doing your calculations, you're like, wait, my sign doesn't make sense for what I know it should be. That's because right now we're from the viewpoint of the thermometer. So this is the amount of heat gained by the thermometer. Where's it getting this heat from? The system. Okay? So let me write that down. This is heat gained by thermometer, which is part of the surroundings. Okay, so the reaction, we already said the reaction is exothermic. The reaction, or the dissolving, is generating heat, or liberating heat. It's exothermic. How much heat is it liberating? 1150 joules. So therefore, to actually calculate the delta H of this solution, it's going to be negative Q of the thermometer. So therefore, what is my delta H for the dissolving of sodium hydroxide? Negative 1150 joules. And that's why for your hand warmer lab, you have some calculations where you have to change the sign, okay? Because you're changing the viewpoint, okay, of where it's coming from. Okay. Okay, so in this problem, say we didn't cancel out the masses. This formula here is a derivation of using Q equals MCAT twice. Technically, what you're supposed to do with these problems is, for the hot water, solve Q equals MCAT, because it's losing energy, and then plug that in for Q equals MCAT for the cold water. Problem is, you can't really solve Q equals MCAT for the hot water because you don't know the final temperature. So that's how we're getting here, because we have a complete transfer of energy. Here, the sodium hydroxide and the water together are producing this energy. Okay. All right. Now, let's talk about the particle interaction here. Since sodium hydroxide is releasing energy, that means it would rather be dissolved. It's happier, if you will. It will go to a lower energy state if it's dissolved in water, if it's, dissociated, than staying together. So compounds that produce heat when they dissolve, they would rather be dissolved than stay together. If for some reason this got colder, that means it would be absorbing energy. We would have had a negative Q right here. It would have absorbed energy from the surroundings. The thermometer would have observed a decrease in temperature, and our H of solution would have been positive, because that means that those particles would rather be together than interact with the water. Like, I don't know, some sort of chromium chloride compound. Okay.
Would it be possible to invent a substance that you wouldn't even have to heat coffee up? You could literally just put the powder in, and it would make hot coffee because of an exothermic reaction.
There are plenty of substances that you could just put in coffee that would heat it up. The problem is they would also make you either violently ill or kill you.
This is $1 million idea.
But the thing is the reason why hot coffee, like taking cold brew coffee aside, hot coffee, the reason it works, or reason why we have to heat it, is because you're removing the like the caffeine, or not removing, but you're getting the coffee stuff out of the grounds. The grounds. Yeah, grounds. Words. I'm not a wordsmith. Okay. All right. Number 20. Number 20. This is like your lab. This is just like your lab calculations. So this is just like number 19, except we're also going to account for heat loss to the calorimeter. Okay? So starting off, it's going to be the same. A little bit different from number 19 in that number 19 is actually, in terms of what we're doing in number 19, is more like your lab where we're just dissolving things in water. Number 20 is we're reacting two things together, and they're producing or absorbing heat. But the calculations here are more like what we're going to do in our lab, and like your post-lab and stuff like that. Okay? So we have two solutions, sodium bromide and silver nitrate, that are reacting together. There's 50 grams of both. They both are starting off at 23.65 degrees Celsius. They react together, and the temperature raises to 25.40 degrees Celsius. So, is that reaction endo or exo? Exo. Exothermic, because the temperature went up. Because the thermometer is not part of the system. The only way the temperature to rise is heat has to be coming from somewhere. The heat comes from the reaction. So we have an exothermic reaction. It's producing enough heat to make the thermometer rise by like 1.75 degrees Celsius. Okay? Some of the heat is also lost through the calorimeter. We're told the heat capacity of the calorimeter. Your lab calculations walk you through how to calculate the heat capacity of the calorimeter. Okay? So we're going to have to do two calculations here. One, I think there was a pre-lab question like this. One, you're going to have to calculate for the Q equals MCAT from the standpoint just like we did in number 19. Then we're also going to calculate the heat loss through the calorimeter using the heat capacity. So let's first deal with the reaction, the heat of the reaction. Who's observing the heat of the reaction? The thermometer. So what's going to be true about the sign for this? It'll be positive because the thermometer is gaining energy. So Q equals MCAT. What's our delta T? Our final was what? 25.40. What's our initial?
23.65.
So what's our delta T?
1.75. No, 8.
No, 1.75.
All right.
2 decimal places. I know, you almost did. All right, so Q equals MCAT. What is our M for our reaction? 100 grams, because we have 50 grams and 50 grams. We can ignore the concentrations. It's actually 100.00 grams. What is the C of our solution? Four point what? 4.20. In the last problem, we were dissolving so little sodium hydroxide, then we were able to assume that the C of the solution was the same as C of water. And that's also going to be how you're going to do it in your lab. You're not going to be dissolving a ton of your salts, that you can assume that the C's of all of your solutions are 4.18. But this one, we're assuming that's 4.20. Okay. And then delta T is 1.75, right? So what is the Q of the thermometer? 735 joules. Now, some heat was lost through the walls of the calorimeter, maybe out the top. So really, our temperature should have been higher than 25.40 than what we actually measured. It really should have been higher than that. So really, we should have observed more heat from the viewpoint of the thermometer. But we didn't, because some of it was lost through the calorimeter. So let's calculate that energy lost through the calorimeter. And that's going to be this formula. Q equals big C delta T, where big C is the heat capacity of the calorimeter. Okay? So Q equals, so this is Q lost, equals, big C is 65.0 joules per degree Celsius. What's our delta T? 1.75. So Q lost is what?
That can't be right. It should be around 110. Yes.
Oh, you forgot the decimal? All right.
Wait, no, that's still not.
I don't understand how forgetting the decimal. I feel like that would have, I don't know, whatever. You typed something wrong. Because it's just it's basically for every, this tells you that the specific heat, the heat capacity of the calorimeter tells you for every degree that your solution changes by, that's how much energy it's going to lose. Like how much energy it'll transfer through the calorimeter. Okay? So now, what do? Add them. Because this 114 joules was still produced by the solution. That's how much the calorimeter lost. That's how much that's how much more the thermometer should have observed. But it didn't, because it was lost through the calorimeter. So to find the total Q total, we're just going to add them. So what is that? 849? So that's how much the thermometer should have observed. So how much did our solution lose? Or how much was produced by our solution? 849 joules. So what's our delta H of our reaction? Negative 849 joules. Because 849 was produced by our reaction and observed by the thermometer, or at least should have been observed by our thermometer. Okay? All right, I'm going to stop the video.